This evening I'm going to try and explain how the synchronous detector works on a modern synthesized radio. There's various different forms of synchronous detector. The Sony radio you see above has probably got a fairly sophisticated synchronous detector in comparison with a lot of the British radios around, like the low HF225. I can't vouch for the more modern radios, but certainly the Sony's one works very well. Basically, a synchronous detector allows you to strip out the carrier wave that the transmitter generates, and the set will generate its own carrier wave, and then you can select the upper or lower sideband to get away from adjacent noise. So, as a quick sketch here, if you can imagine this as the frequency range, and we say 500 kilohertz here, so this is a medium wave band, 1500 kilohertz here. Now, if I have a strong signal, say just here, and this is, imagine this is a spectrum analyzer's view of the signal. Let's say this is 909, this is a Talk Sport, and I'm listening to Talk Sport, and I want to listen to Talk Sport, but unfortunately for some reason there aren't any medium wave channels now, but if you can imagine a stronger signal at, I don't know, just over 1 meg, 1000 kilohertz transmitting here. I'm trying to tune here on a normal bandwidth of a radio, which is about, I don't know, let's say 6 kilohertz. I'm getting interference from the adjacent channel because it's so close and so powerful I can't hear what's going on. So what I will hear is I'll hear the channel I'm interested in, but I'll also get a sort of like a distorted sound in the background of the radio, the signal adjacent to me interfering, and that's a real problem. And it used to be a real problem with medium wave, crowded medium wave bands, not just medium wave, short wave as well. So obviously the easiest option is to reduce your IF span. So we've got that's your wide IF there. That's your wide IF, and this narrow here is a narrow IF. Now narrow IF will actually allow me to only receive a narrow bandpass. So straight away we get away from the interference. It could probably still be noticeable, but it won't be as bad as it was, but also our fidelity will drop back quite considerably. What a synchronous detector does is it does two things. Firstly, let's redraw this again, so we're basically the same situation. This is our strong signal that's annoying us at 1000 kilohertz or 1 megahertz. And this is our 909 signal. This is just a sort of like a demonstration. This isn't a known frequency or a known problem. We've still got this signal here, and we've got the signal at 909 kilohertz. And for argument's sake, this 909 kilohertz is very weak, and it's fading in and out. I don't know if people who can remember Radio Luxembourg, if you listen to it at night, you could hear the music would play, and then it would become very distorted, and then it would fade back in again. It would sound okay. Now that's because the carrier wave is fading away, but the modulation is still present, and the radio is struggling to detect the carrier wave. Now what a synchronous detector does is it does away with the carrier wave. It basically mutes the carrier wave, but it knows it's on 909 kilohertz. So what it will do is it will generate its own frequency at 909 kilohertz, and what that does is it allows it to be able to get away from the selective fading, as it's known as. So you're generating a strong carrier wave, and as long as the audio is there, it will allow the audio to come through. So you're generating your own carrier wave within the set, and it will allow reception of the AM signal to come through. As long as the AM signal is not too degraded and the signal doesn't drop back too far, this works really well. But the other thing it also does is it allows you to get away from the effect of the strong signal on the adjacent channel. What's lovely about the Sony sets is that you can select upper and lower sideband. So So for example here I've got this strong signal in the upper region, so there's the upper part of the sideband that's going to be affected mostly. So what I want to do, and it basically looks similar to like that, we want to reject the upper sideband. So what I want to do with the synchronous detector is select lower sideband. So basically what I do is I down tune slightly. When I down tune slightly, the lower sideband light will come on, LSB, and the upper sideband will be totally ignored, and that means all the signal, even though half the bandwidth, will only come through on the lower sideband. So we get totally away from the upper sideband and all the interference from the adjacent channel. And likewise, if the signal's on the other side, we can reject the lower sideband and select the upper sideband. Now, as I said, you can do that with narrowing the IF, but of course you lose fidelity quite considerably. And there are various other ways of doing it with a radio with a product detector or designed to receive a single sideband. You can actually tune to an upper sideband and make a very narrow IF, but it's very difficult to listen to. So basically it's a selectable filter. You can select your upper sideband, your lower sideband, and just get away from the noise. So what I'll do is I'll try and demonstrate this. And what we're going to do is going to go to 909 kHz. Won't get any copyright on that, so that's why I'm using this as a demonstration. And you can hear pretty reasonable reception, and no problem there at all. And it's on wide IF, it's narrow IF, no problem at all. And it's become less and less of a problem as more and more medium wave stations are shut down. But what I'm going to do is I'm going to generate an adjacent channel, and what I want to try and show you is what it would be like to have a strong signal. I'm going to set a signal, let's set it at 900 kHz. So I'm setting the Roden-Schwarz at 900 kHz. I'm going to ramp up the power a bit. I'm going to generate 400 kHz turn on, 1 kHz turn on there. And actually even at 900 kHz it's out of the IF bandwidth to cause any problems. So let's increase the frequency slightly. Okay, that's 902 kHz. I can't hear TalkSport anymore. Barely under the background. So I go to narrow IF. That's come back and I can hear it fairly clearly, but the sound quality is pretty awful. So let's try the synchronous detector then. So we're going to go on to synchronous detector in wide mode. So we'll go back to wide and select synchronous detector. Synchronous detector is running and we're on the upper sideband now. So we're away from the Roden-Schwarz is generating 902, the set's tuned to 909. I'm on the upper sideband, I'm away from the noise. And you can hear that's pretty listenable. You can still hear the 400 kHz tone of the Roden-Schwarz, but it's highly muted. Select a lower sideband. It's awful. It's hard to hear. You can hear the carrier frequency beating with the radio. There's that high-pitched noise in the background, and you can clearly hear that the synchronous detector is doing its job. Let's go back up to the upper sideband. Perfectly listenable. If you want to listen to football, which I don't anyway. But you can see that that's working really well, and it's muting it out. Let's turn the synchronous detector back off. Okay, that's wide. That's narrow. Narrow is quite listenable, but you lose the sound quality. So let's move the frequency even closer. So let's move it to 905. Now, even the narrow filter on the IF is too wide for this, and you can hear that you're interfering with it. So we go to synchronous detector again, wide. It's starting to struggle a bit now, but you can still hear it on the upper sideband. I expect on the lower sideband, and these are the sideband lights here. I don't know if you can see these actually very clearly. These are the sidebands, and we're on upper sideband at the moment. I'm going to choose the lower sideband. And it can't even lock into the lower sideband because the signal from the generator is so strong it can't get a lock. But what you can do, if you've got a if you haven't got a synchronous detector and you've got a shortwave radio that's got BFO on it, or a product detector, you select upper sideband and detune to the right amount. You can actually resolve it on upper sideband or lower sideband. See, that's the lower sideband's causing problems, but the upper sideband we're moving away again. Listenable, but you're down to probably a 600 kilohertz bandwidth, and the audio quality is pretty awful. But you can clearly see the best performance will be with a synchronous detector. So that's that's the only real way I can explain how a synchronous detector works. And it's actually a demonstration like that. As I say, with the modern radios, they probably become much better, and also with the less crowding on the medium wave bands, less and less necessary, I would say. But just a quick run through. This is a Sony ICF 2001D. I've had this for 25 years plus. Bought it off a friend of mine who was left it in a will. It's undergone a few modifications. As you can see, it's got this carbuncle with tuning knob here that's tied to the master oscillator and gives me fine control on all the frequencies, including airband, which I used to use. I used to do a lot of airband listening, and when they went over to 8.33 kilohertz spacing, I used that to fine tune the channel so I could actually still resolve the signal. But brilliant radio. I love these radios. I've got 3 of them, and excellent performers even by modern standards. But that's a run through of the synchronous detector. I hope it was of some interest. Any questions, please ask, and thanks for watching.